Right, I think we are starting broadcasting here. Ben's getting his earbuds set up. Hello, everybody. How are you
Hey,
this fine Friday? Hey, Ben.
good to see you. Always
Yeah,
good to see you, Bill.
morning time out your way, afternoon out my way. Everybody else somewhere in between those. No, that's not true. There's
Well,
people not in the states that watch this.
that's right. Actually, I think it's turned out we've got quite a few people in Europe. So if you're
Right,
watching
right.
from Europe, I hope you're enjoying your Friday evening. And
Yeah.
it's nice to have you here. Everyone, remember you can chat in the YouTube, and Bill's watching that, but I'm kind of half looking at that, and we also have our Discord running in the background as well. So we'll try to interact with you, and feel free to jump in and ask questions or make comments or share some of your own thoughts while we go. That's all part of the fun of live streaming is that it's actually live.
So, yeah,
Um,
Mondo 8-Bit just said he's from Italy. Yeah,
hey, awesome! Well, I
I had
love
no
Italy.
idea.
Have you been to Italy, Bill?
No, no, I've only been to Switzerland and Japan and
I've never
Canada.
been to Switzerland or Japan, and both sound marvelous to me. Italy, I went to Italy for the World Maker Faire Rome
Oh, wow.
in, I want to say that was 2016 as well. I went to a bunch of Maker Fairs in 2016 because I was,
Which sounds not that long ago, but that's 6 years ago. I found a bunch of PowerPoint things today that from 2016. I'm going, that's not 2 years ago anymore.
Tempus Fugit.
It's what?
Tempus Fugit.
I don't know what that is.
It's Latin. Time flies.
Ah, okay.
And that's appropriate because I'm thinking of Rome right now, and that's
Right,
that's
right.
really the birthplace of Latin. So, which is the birth of all the other uh, Romantic languages from Europe, including English. Um,
Right.
so, yeah, make a fair Rome. It was kind of rainy, but we had a lot of fun. There were a lot of people came to the booth and hung out, and I got to meet a good friend, Roberto Lo Ghiaccio. I'm sorry, Roberto, if I still don't say your name correctly, but Roberto was a very enthusiastic user of Circuit Maker back in the day, as I recall, and he actually won from a competition I ran, an Other Mill Pro, which became the Bantam Tools desktop PCB mill. Fantastic little machine. I actually have one of them right here. You can see.
Cool. Yeah.
Uh, that's probably something we can talk about another day. I'm not quite set up for it yet. I actually just recently got the vacuum attachment, so I can have dust extraction. And I was experimenting with building my own dual cyclone dust extraction system to go with a little vacuum cleaner to use
Hmm.
with it. But the vacuum cleaner is way too powerful for the tiny little vacuum head in the mill. So I have to add some sort of bar pipe, bypass air system to it. But once I've got all that going, and it's kind of noisy, but once I've got all that going, we'll do some live milling on the show, perhaps just to show people um, how that sort of goes. And that's what I use for all my prototyping for my little bits of RF printed circuit board that I use when
Oh,
I
okay.
do the RF classes. I have one
Right.
coming up soon at PCB West in Santa Clara. So if any of you are in the Bay Area, the San Francisco Bay Area, in early October, there is our whole hardware professional PCB design industry conference, the premier conference, you could say. That's the wrong word, but people use it this way. Um, is PCB West, and last year it was virtual. This year it's in person again, and I have the privilege and honor. They've allowed me to come back and teach a class. Like I love doing that. It's a lot of work to prepare for it and make sure the delivery is good. But last 2 years running, I did an RF PCB design class. This time I'm doing a shortened version because I was with my new job at Autodesk and I knew I'd have very limited preparation time. So I thought, well, the one thing I never got to, which I always wanted to get to in RF and microwave PCB design, is the antennas part. And I never seem to have enough time in the 1 day or half day courses to get to antennas. So this time I'm just going to do only PCB antennas and talk about that, and it's only going to be a 2-hour session. So so I'm really looking forward to that. So I wasn't actually even intending to talk about this, but I thought just since we were talking about presentations and things that and the other mill made me think of it because I used that for prototyping PCB antennas. This is
intentional antennas, not the other kind.
Yeah, this is a Vivaldi antenna.
Yeah.
These are benefit. The major benefit of these is the ultra wide bandwidth. That's why we have them, and directionality. Brilliant invention. So we'll be talking about all that sort of stuff. But I use the other mill, or the Bantam Tools desktop PCB mill, to prototype these things. Oh, check that out. That's a serious Vivaldi.
900 meg to 12 gig.
See?
So yes,
See?
on the wide
You want to talk about wide bandwidth? Yeah. Vivaldi antennas.
And good ones come with the charts.
Yep. And I've noticed they've become very popular in audio systems. I've seen we have at my church we have in-ear monitor systems, and for the musicians we have all wireless microphones everywhere, and they use Vivaldi antennas because you have a big stage, you've got directionality, but you put the Vivaldi antennas somewhere near the back of the room on the back wall where there's plenty of room for the beam to cover the whole stage area. So they're really good for concert halls and things like that. And the wide bandwidth means you can share one antenna with multiple different systems. So the antenna goes to a kind of a multiplexer that allows it to transmit and receive. So it's transmitting for the in-ear monitors and receiving for the microphones. And it's got such wide bandwidth that all of those devices can share that antenna, and they're all on different channels. So it's pretty marvelous kind of antenna, the Vivaldi.
Right. I just found this in my collection, and I don't remember getting it. It's a 2.4 gig, and it's got what I call directors on the front of it, but they're just stubs spaced in a way that reinforce. If it acts like a Yagi antenna, that those would be directors.
Yes, I would say.
And then there's a reflector behind the element. Yeah,
that's definitely a variant of the Yagi. The Yagi uses
Yagi Una. Yeah.
Yagi Una uses passive elements.
Right.
That reflect and radiate in.
It's complicated. Yeah.
They reflect and then re-radiate in phase with the signal at the band of design.
Right.
But they give you very strong. So it's still a narrow band antenna, but it gives you very, very strong directionality.
So for TV antennas, like going back to the 70s and 80s, the regular old NTSC antennas, those were a lot of times Yagis. And they were to combat the narrow bandedness, as you're talking about, is why there's long ones at the back and shorter and shorter and shorter, so that they're staggering. And then the beauty of the math, I'm told, because I can't do the math, is that this thing that acts as a director at one frequency is a reflector at another frequency. So the math is very intertwined, that all these elements, passive elements, act as amplifiers, reflectors, and everything across a wider band, but while maintaining the directionality. So I grew up with a rotor, sitting on the TV desk
Oh,
or on
so
the
you could
TV top.
turn.
Turn the antenna. And all the places we were in the country in Indiana, everybody had their own little tower, the little the aluminum steel tower, I mean.
Yep.
And you had your rotors, and you would point towards Indianapolis or towards Muncie or wherever the station was coming in at.
Yeah. That's that was the advantage of living a bit further away from the city, was that you could just, and in Sydney where I grew up, most of the television and radio broadcasters were clustered, and I think they did this deliberately in the 1920s, when all of these Sydney was a much smaller city, but the broadcasters in AM radio and the city planners, they kind of clustered them all together in one place, and they grew from there. But because of that, you could just, I lived way
point
far
it in
out
a general
in the city.
direction.
Yeah, we only needed one antenna that had the multiple elements for the different frequency bands, UHF and VHF, and then point just in the general direction. We got pretty good reception.
Right. So my memory is our antennas, then the UHF pointed out the back, so you'd have to swing the whole thing around to then you point the UHF band to Indianapolis, for example. So remember, you'd see this kind of arrangement in the front, and then the back had its own UHF bow tie kind of hanging off it.
Right. And
so we hated UHF.
Was it very hilly? Did you have
no, it's Indiana. It's flat. My ears still pop if I go up like 2 flights of stairs, because I grew up with no elevation changes in my life.
That was also an advantage. You could have decent UHF reception.
Oh, we had over 60 miles for VHF. Yeah.
In Sydney, there was one UHF channel while I was growing up, Channel 0, called SBS. It was a government-owned channel. The government owned 2 channels, the Australian Broadcasting Commission and SBS. The ABC was on Channel 2, which was all the others were VHF, but SBS was UHF, and it wasn't until the 90s before we got a new antenna that was good enough before, and the TVs actually then became better. We got a new TV, and the TV had a more sensitive
front end,
and then finally we could watch SBS and get some of the British, police shows and stuff that they had there that were unique. But and some of the other, SBS also had a lot of documentary type stuff and current affairs type stuff that was hard to get anywhere else. And but when I was little, we couldn't watch it because we were too far away, and there were too many hills and valleys between us and the transmitter. So anyway, because UHF doesn't go around corners like VHF does a bit better. But
no, and we would watch spooky movies on a Friday night unless a storm rolled in, and as kids we'd be sitting there watching the spooky movies fade in and out and just become totally unwatchable due to just storm interference. So,
yeah, we also got constant ghosting from aircraft. That was another annoyance.
Well, talk about why aircraft causes ghosting. What's the key word there that would make? Because an airplane seems small, so why it's not blocking the signal? What's it doing?
It's reflecting it.
Yeah. So you get multipath. It shows up in a different length of time, and so it's out of phase from the signal you want. And you can watch it beat. It'll go whop 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 whop, and then get clear again.
Yeah. And it was noticeable with analog TV, but digital transmission techniques totally eliminated all of those old problems.
Right.
Because it's like echo cancellation in the Zoom call, right?
Right.
The software can tell, there's an echo, and ghosting was an echo. It was an echo of the RF signal. So yeah.
You just remind me, because we got airplanes flying over central Indiana, headed for some Air Force bases in Ohio, and you know what we grew up with was sonic booms. before they were outlawed.
Oh.
So you'd hear boom,
Oh, that's
boom,
cool.
boom, during the day. You just know, and I've seen a B-58 Hustler flying in the sky and stuff. It was real cool, but it became annoying after a while too. And then
when
they
people's car
outlawed them.
alarms keep going off, or windows keep getting cracked.
I was gonna say there were no car alarms back then. Yeah.
Yeah.
Power steering was actually kind of novel back then. There were still cars without power steering.
Oh yeah. I learned to drive on those.
Yeah.
So what are we looking at there? This you've got the PCB Way 4th PCB Design Contest open. Tell us about this, Bill.
Anson Bow just got hold of me through Facebook, but you know more about this than I do, actually, and we'll find out why here. But for people interested in designing something and winning some money and accolades of your fellow cohorts, they're having a contest. It's the 4th contest. It was hard to find. I had to Google PCB Way contest and then click on the 4th PCB design example. And one of the judges, turns out I know, here is our own Ben Jordan, right here. So, which I didn't know till just right before the show started. But look at these prizes. It's $1,500 cash, $200 coupon, plus a Raspberry Pi.
That's
and
amazing.
just for doing it, just for that participation award, you get an ESP32 IoT development board.
Wow.
So,
one of these. Just like this one.
Hang on, let me make the screen smaller. There you go.
Right?
Yep.
I love these things. This is a dev kit one, by the way. I think the one they're giving away is a newer revision of this, but it's pretty much exactly the same thing. These are amazing, easy to use, indispensable. But okay, so this is obviously a
I was
big
going to say,
market.
I just happen to have the argon. This is slightly different. By the particle, argon and xenon, sitting on my desk here for no other reason than they're sitting on my desk. These IoT development things come with so much. They come with Wi-Fi, Bluetooth, the multiple WAN technologies all built into them, and you really can mesh the heck out of them.
Yes. Yeah. I actually got sent the particle kit as well, like what you're showing there, some time ago, and I intended to do an intelligent raised garden bed watering system because my wife wanted these raised beds, right? So I made the wood frames and everything, and my intention was always to make it IoT, like have at least an Arduino or something controlling watering, but I wanted to measure. I wanted to do precision agriculture, so I wanted to measure the soil moisture and have a control algorithm to maintain the soil at a constant moisture. But then I realized, well, not every plant likes that. They probably don't want constant. They probably want some seasonality and variance that helps them grow, right? But
the roots have to dry out. Yeah, you can't just keep them wet. I don't know much about plants other than I've killed my share. My wife has killed more than me, so I'll say that at least I can raise a couple kinds. But now this is our first year we have tomatoes growing in the garden.
Oh, that's cool.
Yeah.
You'll have to make your own spaghetti sauce.
And we even keep the chickens out of it this year. That's why we have tomatoes. We found out they were eating the tomatoes.
Tomatoes used to be the cover, in Australia at least, they used to be the cover for marijuana. If people were illegally growing weed down under, they used to plant it with tomato plants because they're in the same, either the same family or they look very similar. So from aerial photography, if they see little red dots here and there, they'll go, oh, it's okay, they're just tomatoes.
Right. So so everybody check out the PCB Way design contest. You're wearing, did we talk, I forgot if we talked about your shirt on the air or off the air, but you're also, that's an old one, but speaking of Hackaday and prizes, Hackaday's currently running one of their prizes.
This is my favorite one because it's got Nikola Tesla on it.
Okay. Yeah. I never got one of those.
Yeah, I think this is from 2016. Someone gave it to me at the Open Source Hardware Summit that year.
Okay.
Sophie Kravitz, I
Okay.
think. Our friend Sophie
Yeah.
gave it to me. Yeah,
Sophie. Yep. Yep. And we've had her on.
So last week
So
we were talking about your presentation from c128.com that you did at the VCF.
one of the VCFs. Yeah.
One of the VCFs, but we ran out of time. We didn't get to finish. So
Right.
where were we up to here?
So yeah, let me make this bigger for a second. And what we had gone through was I talked a lot about the different kind of cartridges that were available for doing diagnostics out there. And we started by talking first about simplistic things, and then about checking the power supplies. And it's check, check, check when it comes to the supplies. Unfortunately, with power supplies, just putting a volt ohm meter on there may not tell you exactly if the supply is completely good, if the volt ohm meter can't detect ripple and things like that. If you have a volt ripple on your 5-volt supply, it's not going to work. So unfortunately, there is a time when oscilloscopes are useful. If you're working with a CRT, the good news is a lot of times you can tell if it's working just by the smell and listening to the high voltage crackle and whether the hair on your arm stand up or not, you know? So
That actually does, it makes my hair stand up for psychological as well as electrical reasons.
now, have you ever had to discharge a picture tube? Have you ever done that?
I've never done it using my body.
Yeah, but I mean intentionally with a cable and a screwdriver.
No, I've never had to. I've never been in that situation. I have had the back covers off them and just let them sit for 10 minutes and dissipate, which
that on the newer stuff there's a bleed off resistor, but on the old stuff, because I came up through the ranks as a TV repairman, you could hold a charge for a day and enough to charge to knock you on your ass. So I would actually not only discharge it, which is where you take a nice lead, a good ground lead, put it on the chassis, hook to a screwdriver and go under that P2 anode button, and make sure that nobody's used the screwdriver as a chisel where they hammer on it. Because I've seen screwdrivers where the metal sticks out the back. Well, guess what happens if that's the screwdriver you use going under the P2 button? But my thing was I would leave it under there, because if you discharge a tube and wait a good minute or two, go in, you'll get a second pop due to the dielectric, the charge redistribution in the dielectric. So even though you discharge it once, you can usually get a second pop out of them. Now, I did one time leave the screwdriver in there, but I caught it right away. In the days of tube high voltage sections, it didn't hurt it, right? I left my shorting thing in there. But had I done that to a solid state high voltage section, I would have popped the solid state section. So that's the danger.
Sure. Mm-hmm.
Yeah, they're only useful once in that mode of operation. So we went past that, and we had just gotten to after swapping the chips. Actually, we did skip some too. If you guys
you're talking about just swapping out all the chips to see, basic.
Right.
This board is good. This board is not good.
Yeah, and I was, people that do a lot of diagnostics even today, they have a set of chips. I know Rob Clark does for the TED series. I know Ray Carlson probably has known good chipsets they can swap in. The common culprits in the VIC-20s, RAMs easily. Common culprits in the C64 for me was always the PLA, because they were made badly. I gotta believe the PLA is a programmable logic array. It's not the brains of the outfit, but it's the roadmap that makes all the I/O work and everything.
The glue logic for
it's the glue
memory
logic.
Mapping and switching things out. Yeah.
Yes. Yep. And we had a problem in the manufacture. We were including too much boron in the mix, and I don't know if it was in the passivation layer, but we were getting failures in the passivation layer, which is the coating of silicon nitride that sits on top of the chip that basically acts like RTV. It tries to protect it from the environment, keeps your chip from getting wet and whatnot. And
Yep.
we were getting holes in that, and you could literally see crud under the microscope. Once it got under there, it would spread under this clear passivation layer, and it would be purple. We called it the purple creeping crud. So Commodore 64 PLAs were bad. The SID, I don't know that they fail more often, but it's an analog chip with some weird uses. It's not just a digital chip. And then the filter capacitors on the outside of the chip, if you turned off the SID suddenly, there could still be a charge on those filter caps. Well, where they drain through, they're going to drain through the now unpowered SID chip. So I always felt that some of the SID failures were due to the fact that there was no current limiting resistor or a strap diode on these filter caps.
Wow. And that's on the audio analog output of the SID,
That's
right?
the audio, right.
Just in case anyone is watching who isn't as familiar with C64, I assume most people are, but the SID was the sound interface device. These, even today, original SID chips, if they function, will sell for a lot of money on YouTube, on eBay, because some homebrew synthesizer makers just love the sound of them. This 8-bit, but it's not sampled, it's synthesized. They're 8-bit chips, but they actually have analog synthesis.
They use a sine table to drive it. Yeah.
Have a sine table. They also have FM. Correct me if I'm wrong.
Yep. And then they had 3 dB filters, true RC filters, built into them.
Yeah. A whole bunch of cool analog stuff, all digitally controlled, and that's
right.
It's exactly what a lot of classic electronic music producers love the sound of them, and there's a lot of clones made with Atmega, AVRs and things like that as well.
Right.
But they sound
amazing. We needed a human to do the test for the SID chip, even in our mass quantity productions where we're making millions. We used loopback plugs. We could exercise the keyboard or the joystick ports and all the different I/O ports. But when it came to the audio, we didn't have any kind of sampling technology that said, oh, that's a distorted sine wave, not a real sine wave. So there was somebody that stood there as they came down the line and, and next.
They had to listen to it and say, yeah, that sounds right.
Yeah, we didn't have a way we could detect gross errors, but that was about it, There was nothing that said whether it sounded good or not, sounded broken or not.
If I wanted, so I've asked you this before, and so forgive me for asking again. If I want to get hold of a SID clone, where do you recommend I go?
I don't have a good answer for that. Rob Clark knew a bunch back when we did this. Let's see if I got SID clones. There are some different approaches to SID clones. I remember that, but I don't have a good... And my knowledge was from back when we did it back in 2010, so I don't have a good answer. So I don't know how much people stuck with the clones they came up with or not.
Yeah.
So we used a slightly different SID in the C128. We used an HMOS 2 version. I think it even runs off a different voltage. It's like difference between 12 or 9, but don't quote me on it. But it didn't sound the same, and part of that was the designer of the second SID. Somebody just posted FPGA SID.
I've heard of that one.
Tosca.
I was looking around that one when it came out and got real excited, and then felt that the owner of that project was that one's good because it's kind of become a shrink wrapped product. So if I'm a synth builder and I don't want to spend time doing the FPGA coding or messing with it, I can just buy one of those and plug it in. They're a little pricey though, I've got to say, and and they're not open source, from what I can tell. Not open source, so I can't just go build one using the FPGA, a different FPGA chip that I know I have access to more readily or whatever. I've heard of the ones based on Atmel or Microchip microcontrollers. They might be open source, but I'm looking for something like that I could just build one and see how well it works. I'm happy to support the project if someone's put a ton of effort into it,
We could
and
make it an
and
entry
they're
on
selling
PCB
them.
Ways contest.
Yeah, and they're selling them. I'm glad to support those, small business
Right.
entrepreneurs doing electronics. I'll support them.
So do you know what
So,
happened to the designer of the SID? Do you know where he ended up after Commodore, by any chance? Do you remember the keyboard company called Ensoniq?
no way. That's right.
Yep, that's
You
them.
have told me this. You
Yep.
have. Yeah, that's right.
Yeah, they were full. A lot of Commodore people in there, MOS people. This
That's probably why the creative Sound Blaster
Swin
cards, there
SID.
was some of the more advanced creative Sound Blaster cards, although Creative was a Singapore based
Right.
company,
They did.
and
They did a like Turtle Beach or something. One of those
they
companies was
collaborated.
also the same guys. Yeah.
There was some, and Sonic did some chip design, I believe, um, for the creative Sound Blaster Lives. The main chip design, I think, was done by the Ensoniq people for the
Yep. Yep.
10K1 chip, which is probably why it had such great synthesis capabilities.
So now, in the old back when we did this, one of the PLA replacements we had was, and so this is old. So I don't. There's got to be so many ways to do the PLA these days. But we just happened to show this one back in 2010, made by Jens, who did this. Actually, he was working with Jerry Ellsworth on the C1 project, and he did a
Uh-huh.
super PLA replacement. So list of resources. Here, I'll pull it up real quick, but they're ancient. You can do a
So,
freeze frame
hey,
on
Bill,
that if for people
can we
that.
post can we post those links in the Discord or on our CoriolisEffect.com?
Yeah, let's do it on Discord. Let's make them come to us, to the party, so to speak. So yeah, if I dropped him, I don't know how well that. Yeah, somebody just mentioned Bob Yanis, who's exactly who I'm talking about.
Yeah.
So after swapping the chips, requires an oscilloscope, as I was kind of alluding to. For if you're trying to repair a microprocessor based product, it gets real hard to do it with just a voltmeter.
Oh yeah.
Power
You really
supplies.
want to scope, and if
Yep.
possible, a logic analyzer scope would be even better.
Yep. Yep. So even power supplies, even the way they turn on can be significant. If a power supply jumps up to 4 volts, drops to 2, and then up to 5, you could have already crashed your processor. It might not come on.
And
So
this
it's
is
called
why,
non-monotonic when that happens.
yeah, this is why modern system on chip, SOCs like the Freescale I.MX series, the big, powerful, hulking, giant, low power consumption but very fast devices they're targeted for automotive applications, but they find their ways into a lot of other products because they're very easy. They have really good coding ecosystems and they're very easy to develop for. And so you could have one chunky microcontroller with a bunch of DDR4 memory on a Raspberry Pi sized card,
Right. Right.
build a custom embedded system. All of these require power on sequencing with a separate
Right.
chip that controls. Sometimes it's built in, but there used to be done with a separate voltage regulation control or power management control chip. This is exactly why.
Right. Right.
Yeah,
Yeah.
and you
Yeah.
have to
It's
power
almost like a
different
power
sections
supply
of.
on the
Yeah,
chip. Yeah. On the chip assembly. Yep. Yep. Very important. Ripple, we've talked about that. If I make this a little bigger, this is a no-no. You shouldn't even be able to see the ripple. If anything, you should see digital noise, but not the ripple of the AC, the 60 cycle or 50 cycle, depending on where you're at. So care and feeding of the microprocessor, and this is kind of where we left off last week.
yeah.
So when I turned on the recent 6502 thing that we had shown here with the cool vacuum fluorescent display, code by Frank Buss, I had done these to make sure everything, when it didn't come on right away, I got in and made sure the power supply was monotonic and that it was clean and that it powered up. And then I checked the clock to make sure it came on and didn't jump to a high frequency and then drop to a low frequency. I've seen that where clocks will start at a third harmonic, so suddenly they're at 12 megahertz and then drop to 4. Well, during the 12 megahertz, you crash the processor. It's already too late again, even before things start. So you need a clean startup on your clock as well as a clean clock. And then the reset. Again, reset needs to be a nice clean pulse. It can't be a pulse that goes up, down, and up again.
Yeah.
And as you mentioned on the SoC stuff, they're generating their own reset pulses from the power circuit themselves these days, for that reason.
Just on that non-monotonic power on, that used to happen a lot with devices
Switchers.
like, well, but also with devices like the Commodore 64. Your power switch was not on the mains side, it was on the low voltage side. So you have a big lump of power supply off your offline. It steps down using a transformer or switching regulator down, switching power supply down to your different voltages. But then there's an on-off switch, and the on-off switch is bouncy, and this is why it happened, right? So. So, today we'd do it differently. Today you still get bouncy switches. There's no way of avoiding that. But if you have something that's got USB charge and battery powered, you have soft switching circuits. So this gets into point of load switching, and you use little soft latches that switch your main pass P-channel FET on to provide power to the circuit, and that's a good way of avoiding that problem.
Right. Yeah, Thundersqueak mentioned that some of the old switch mode replacements are, she says, noisy, too noisy. I'd say maybe even the wrong kind of noisy to get some of the older computers working.
Wow.
I see it looks like ZX Spectrum. And I totally believe that. The power on characteristic of Chris mentioned PMIC bootstrapping, which is funny because you and me spent the pre-show talking about bootstrapping.
Yeah.
And that is where we used to see it. It's not just a lump charge coming up nice and, not to overuse the word, monotonically. Yep,
totally.
So.
Yeah, I've always been skeptical of those 7805 DC to DC converters replacements.
I used one of those actually with Mike Fikes. We didn't know how much current something would take, and so I couldn't do the actual thermal equation. So we threw in a TO220 replacement. It worked. It was fine. And then we found out that we were truly in milliamps range, not in amps range, and we went in and replaced it with a real controller. But what was funny is Mike showed it up on his conducted tests. All the conducted noise went away when we got rid of the cheapo TO220, fake voltage regulator. So it was very usable. But if you want quiet, or if you want real low currents, real low quiescent currents, there's a time and place for linear stuff.
There is. And it's kind of funny too, because it's easy to fall in the trap with linear regulators of assuming that they are unconditionally quiet.
Right.
But that what they actually are, if you, this is probably a topic for another live stream. We can actually look at the internal circuit of a linear regulator. We should do that sometime. Right. But what it is, it's a sense amplifier or error amplifier. It's a standard, typical linear system with feedback. You have an error amplifier. You have a main gain element, which is your series pass device, and you have a reference, which is your input to the error amp. You have a voltage reference that this is your set point. We want the output to be 5 volts, so we have this input that's set at this point, and then we have some gain in the system to get 5 from whatever this reference is, which is usually something like, 2.5 or whatever.
Right.
And it has feedback built into it. And anything that has feedback has a transfer function that determines its response to changes. And the load becomes part of the transfer function. So if your load changes, or if your load has some wacky characteristic, like the load isn't just a resistor, the load is a tank circuit with resonance, which is usually closer to the truth, or the load has inductance, capacitance, and some nonlinearities, that messes with the feedback within the regulator, and the whole thing can become unstable and start to oscillate.
It can become an oscillator, yeah.
Yeah.
And so when you see like the little tantalums, we loved the tantalums of the day, especially when they were on 0.1-inch centers. That wasn't for
like
ripple
match
control. Yeah, especially when they burned up like a match head.
Yeah.
But there's a pole in that feedback and that error amp you're talking about, and you need to move that pole somewhere out of your way. And so those capacitors had to go right across those terminals. They again weren't there for filtering. If they were there for just ripple control, you could put them anywhere almost. So we used to actually draw them in a different way. We didn't draw those capacitors going from the output or input of the amp to ground. We actually showed them going to the center terminal and then to ground. So that was a cue to the engineer, the technician. These are right across the device, not between the rails, but between pin 1 and 2 and 3 and 2,
Yeah.
So,
yeah. So you need to add additional external compensation components sometimes to, once you've learnt about your load and the source, to slow things down or move those poles, as it were.
Right.
That's exactly what we're talking about.
Right. And then on the low LDOs, the quality of the capacitor, I debugged something for somebody a couple years ago where when he got down to 1 volt in to out differential, and it was an LDO designed to do that, it would oscillate. You could hear it in the audio. And I traced it to, they had bought new electrolytic capacitors without understanding the need for an ESR value. They thought more expensive was better, and what they didn't quite realize was, actually, more expensive capacitors tend to have lower ESRs, but there's no guarantee it has the low enough ESR. ESR meaning equivalent series resistance, which is a pole. It becomes an RC. Think about it. If you have a resistor and a capacitor and a signal, as the signal changes, if there's a resistor to the capacitor, that signal will always lag a little bit from real life, and that's what we call a pole. That piece of, so it's not only filters, it's a deviation in time is the way I think of it. It's behind the time, and if it gets far enough behind the time, if you have an amplifier with phase shift, it's an oscillator. If it gets 180 degrees phase shift, it'll oscillate.
So you could say that amplifier was unfashionable.
Yeah, but what was funny was putting the right caps on it, and then it worked again. Yeah. So going back to care and feeding on the microprocessor, what I showed on this slide is basically you give it 3 clean some inputs, which is the clean 5 volts, the stable clock, and the clean reset. And then you look for some outputs, and they were your address lines, data lines, read-write line. And then the chip select logic would take all of that, would take the address lines and give you your first chip select. Let's see what my next slide is, see if I talk about that. In a microprocessor-based system, very first thing a processor does, he wakes up and he goes for a reset vector, which is where he's to jump to in memory. So he goes to the ROM. So we need to look at the addresses. In a 6502, it'll output FFFC. In a Z80, it'll output 0000. And the chip select logic is what turns that into this little pulse you see here. So the very first thing you see is a good ROM chip select. And when I was debugging this thing the other day, I did not have a good ROM chip select. It just was non-existent. I back up from there, and, well, the address lines were non-existent. So I troubleshot why the processor was acting like a dead bug, basically, and found that I didn't have one of the inputs tied the right correct direction. After the ROM, though, some other things will start happening. We do start seeing some RAM happening, some I/O chip selects, and sometimes you might get only a little way into this. If you had bad RAM, you might find your vector. You might even execute some code, but let's say address line 7 was no good on RAM. You could execute some instructions, but once you get high enough in memory, it goes, oh, A7 is shorted to ground. You don't get the full memory. So you'll actually see these things burp and stop. And so the way I troubleshot was you trigger the reset on your scope, and then you use your other probe to look at address lines. See, did I get 12 cycles? Did I get 200 cycles, right? Did it run? Yeah. If it runs for a second and dies, pretty much everything works. I mean, a second is 1,000,000 cycles. That's forever, right? So, but if it ran for 20 microseconds, that's 20 cycles. Okay. Something early on in this thing wasn't working. It's going to be RAM, ROM, I/O chip select, or a funny short somewhere. Let's see if I even show the shorts here.
Yeah. Well, along this line, like when I remember even learning this stuff with a 6502 single board computer that we had to build in college. And the first thing our instructor wanted us to do for that lab was, don't leave all the other chips out, only socket the CPU, and all the clock and reset circuitry was hard.
Right.
Hard soldered and hardwired that in first, measured it with an oscilloscope. Yep, it's working. The reset line goes up after the right amount of time with a one-shot delay. And but then put the CPU in and hook up the whole 16-bit address bus to either a logic analyzer, or even we just had a way to reduce the clock and hook up the whole address bus to 16 LEDs in a row on a benchtop sort of one of those modular things they used to have in the electronics labs, right?
Now, were you able to single step it in that instance? Because the LEDs they'd be moving way too fast to be useful if you're not single stepping it.
That's right. Well, that's why it'd slow the clock down, and we could see them flickering.
Okay, so you would actually slow the clock. Okay.
Yeah.
And there's limits on some of the older processors that weren't CMOS based. There were limits how slow you could go before the charge would drift off on the internal nodes. A 6502 could only go down to, I want to say 100 or 200 kilohertz, something like that. It might be slower than that, but you couldn't go very far down the scale. You couldn't go down to 1 hertz or 5 hertz or anything like that. So
that was an advantage of, I think it was the original Intel 8051. You could single step it. I know we couldn't single step. We couldn't slow the clock down to 0 with a 6502, but I'm pretty sure we could do that with an 8051.
Right. So on the 6502,
the entire architecture of the 8051 was static.
Right. So the way we single stepped in the old days on a 6502 is we used the ready line. I think it was the ready, and so we would tell it execute one instruction, and then wait. And so the clock is still running at a megahertz, but we've told the processor execute just one instruction and stop. And that's how we used to single step. We used to do our development on a thing called a Rockwell System 65. If anybody's ever heard of those, that was my first emulator back in the late 70s. And it was a cool box, big, heavy, honker box. I say that because I used to take it home at night, and I would, show up with bruised ankles from hefting this thing up my steps to my apartment, and then bring it back the next morning. But it was a lot of work, but it allowed me to sit at home and do what you could do in a hardware lab. So I loved my Rockwell System 65. So,
Bill, I can't believe it, but we're already 8 minutes out from the hour.
Yeah.
How does this happen?
Yeah, well,
we must
good.
be talking about stuff that's interesting to us, right?
To us, at least, yeah. Yeah. So one of the things, though, when you do scope things, it's going to look like garbage. If you just put a scope probe on an address line or a data line, if you're not triggering off of a known source that means something to the processor, the scope's not going to mean sense to you. So in a 6502 or on Z80s, 8086s, there's usually a clock period that's important. On the 6502, the falling edge of Phi2 is the money time. That's when data gets latched on read and write cycles. It's when the address cycle has been stable for a while. So what I'll do is I will trigger off the clock, and I ignore all this stuff in here. If I'm triggering off the rising edge of the clock, this is going to be garbage in a lot of cases. Depends on the bus architecture. Sometimes the garbage is out here on the low side. Sometimes if you're splitting the bus and sharing it, if the processor itself is on the high side, he has to come onto the bus, which is garbage, and it looks like ringing sometimes even, and then it'll stable. So we learn to look at a known point in time and say, well, what did the processor see? Did the processor see a 1 or a 0? Whereas if I just looked at it on the scope, I'd see all these other variations in here, and they would freak me out. So knowing when to look at valid logic is real important. Now, one other thing with address lines, and I've troubleshot a lot of shorted address lines, a lot of shorted data lines. If it's, when chips break, they can short their inputs together. But if it's something on the PC board breaking it, usually it was a short, right? It was a piece of solder, piece of wire, or something. And what happens when you scope them, remember, then we trigger off this known good time, the quiet time in life, and we want to see a high or a low. Well, what you would do a lot of times is you would see something at 1 volt, 2 volts, 3 volts, something like that. And it would even change. You'd see it go to 2 volts for a while and then jump to 4 volts. Well, that's probably 2 address lines shorted together, for example. And so when both are high, you get a high. When one's high and one's low, you get somewhere in between. And you see them do this dance that look funny. That's a shorted address line on a scope. It's not going like this.
A very crude D to A converter.
It is. You've built, and unfortunately, you're using the outputs of the 6502 or the ROM or whatever.
And
you're taking outputs
that are overheat, if not burn out.
Right. They're meant to drive 1.6 milliamps, not drive into each other till they can't drive anymore. And so, oh, by the way, my favorite technique for fixing something, fingers, especially back when I had all of them, is temperature. I should have had this in the slide. I automatically, to this day, will sit there and keep feeling chips around.
Yeah, I do the same thing.
And you don't even know what temperature they're supposed to be. If one is warmer than the others, that gets my attention. And then if it's like, well, there's 6 others just like it, and they're not warm, why is this one warm? And so, temperature of, and nowadays they have little thermal cameras and everything. And I was watching one of those, the Signal Path or whatever it was, where the guy used his thermal camera, found a shorted chip. And I was laughing because I'm like, actually, my finger technique would have worked on that. I would have felt that, and I would have felt the heat.
You might occasionally. I've done that and burnt myself.
I had a backwards imprint of the TI logo in one finger because I felt it expecting it to be cold, which is different than feeling it expecting it to be hot. Because when you think it's hot, you go like that. When you think it's cold, you just So I literally had 3 sides of a chip on my finger at one time, and it was that finger because that was the finger I used.
TO220 voltage regulator on a breadboard, and the circuit not working properly, and just gently, gingerly gone like this on the back of the heatsink tab, and smeared the solder coating on it.
Yeah.
And temporarily lost my fingerprint, until it healed up.
Right. Yeah, that was. And so on TO220 cases, the way you can save your figure, TO220 is this case. This is the one everybody sees a lot of.
Yeah.
So if it's got a heat sink behind it and an insulator, one of those little nylon shoulder washers, when they get when they get hot, they get translucent. So if you look at your little bank of heat sinks and your especially audio devices or something, I would look at the color there, and if it's nice, nice nylon color, clear nylon color. Wait a minute, is that hot? And that would save me from burning my finger.
I've never seen that or knew that was a thing. Do they design those bushings to do that? Or it's
they get soft and they get a little translucent. They'd lose that milkiness.
That's good to know. Good to know.
Yeah. And that was back in the nylon days. Of course, now they may have even more exotic, Teflon or something. So, now here's a way. Talking about lows and highs, you'll see during the garbage period here, instead of just highs and lows, you might see a volt, right? And it's like sticking out of the noise. And then when you start looking during our precious, quiet time, we go, wait a minute. I'm seeing either 5 volts sometimes, or I'm seeing a volt. You might be looking at the problem. You might be looking at a blown low driver, where if you remember, it's like a totem pole. There's inside the ROM, inside the processor, is an FET or transistor to pull it high, and then another one to pull it low. You can blow just one of those, and it'll show up. Great pulling high, lousy pulling low, or great pulling low, lousy pulling high.
Yeah.
And the scope will tell you if you believe your eyes, which means you have to make sense of all that chaos in the scope, which is good triggering. It all comes back to good triggering.
It does. And sometimes staring at the wall, right?
Yeah, I've done that. Well, and you know that story, but that's a technique for where I was trying to make sense of the chaos that was being presented to my eyes. Hey, that was the last slide. What good timing.
Wow. 11:59. Amazing.
Yeah.
How does the time just go like this every time? It's good, Bill. It's always good talking to you, and we always learn something new.
So yeah, we'll have to save talking about Bootstrap and the JFET stuff for next time. That you and I started on.
Like I mentioned at PCB West, I'm doing a class on PCB antennas, and I could, maybe after the actual trade show, maybe after that we'll relay some of that stuff.
Right.
But there's always something to talk about. Always something.
It's a big field.
Can I leave you with one thing though?
Absolutely.
If I can bring this up. I did my first. I'm not trying to pitch anything. I'm just excited because I did my first legitimate multi-board project in Fusion. I don't know if you can see that.
There we go.
Yeah. And it came out really awesome. But the cool thing is I can move the connectors around and do joints.
You've got a reminder sticking up in the middle of it.
So they stay together. Yeah, I'm supposed to be receiving a phone call right now, and actually right on time.
That's the phone call.
I better jump off, man. Hey,
all right. Hey, thanks everybody for being here. Thank you, Ben, my friend, and we'll see you next week.